Hello and welcome back to the third lecture of my second course, Feedback Amplifier Analysis, the Middlebrook Approach. These lectures are based on my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online from any bookseller. Following Dr. Middlebrook, I would like to characterize the approach presented here as low entropy formulation of U.S. Patent 2102671, which was filed by Harold Black of Bell Laboratories in December 1937. In this lecture, we are going to develop the concept of loop gain because it is central to all feedback systems. Its importance lies in the fact that it signifies the behavior of all transfer functions of an electrical feedback system. Now, since this is not a course in system theory, we're going to start with the formulation of feedback given earlier by the extra element theorem for dependent sources. We will identify the loop gain inside the feedback formula given by the EET for dependent sources. We will then rewrite the feedback formula in terms of the loop gain, and from there we will come up with an augmented feedback block diagram. We will then rewrite the feedback formula one more time by introducing the null-loop-gain, and finally we will give some concluding remarks. In the first two lectures, we learned that the transfer function of a feedback amplifier can be formulated according to the extra element theorem as follows. Here A is the gain of the amplifying element, AF is the closed loop gain of the feedback amplifier, and AF with A going to infinity is the ideal closed loop gain of the feedback amplifier. And we said that as far as the determination of the transfer function of a feedback amplifier is concerned, this is all that you need to know. What we are going to do now is identify the loop gain inside this formula and rewrite it in terms of the loop gain T. Now we also learned that the same transfer function, according to the extra element, can also be formulated as follows. The closed loop gain is given by the closed loop gain with A equals to 0, followed by this factor here. Now, this is not a very useful form for the determination of a transfer function of a feedback amplifier, such as a voltage gain or a current gain or a trans resistance or a transconductance. Nevertheless, we're going to see that it's very useful for what we are going to formulate next. Now we go back to this formula here and factor out A script A bar and A bar and obtain this expression here. Now when we compare these two, we obtain the redundancy relation that this term here must equal to this term here. And then we go back here and we expand it, and we obtain this expression here. Notice that when we multiply this term up front with the second term, script A bars cancel and we obtain this expression here. When we look at the first term, we recognize that this thing here is the closed loop gain with A equal to 0. Hence, we write that expression as follows. The closed loop gain AF equals to the closed loop gain with A going to 0 multiplied by 1 over 1 plus AA bar plus the closed loop gain with A going to infinity multiplied by AA bar divided by 1 plus AA bar. Now this expression is not only applicable to a voltage gain, a current gain, or a trans resistance or a transconductance, but it is equally applicable to the input impedance or admittance or the output impedance or admittance of a feedback amplifier circuit. So we write it in general as G of F equals to G0 times 1 over 1 plus AA bar plus G infinity times AA bar over 1 plus AA bar. In it, G's infinity is defined as the closed loop gain with A going to infinity, and G0 is the closed loop gain with A going to 0. Now here's where we introduce the loop gain T. The product AA bar is defined as the loop gain T. Now notice that a bar is not a function of a. So whenever we say a goes to infinity, we mean that the loop gain t goes to infinity. So now we're going to take this expression and substitute it in this one here for a bar. And so now we arrive at Middlebrook's first formulation of the feedback formula in terms of the loop gain t. In it, g of f is the transfer function of the feedback amplifier circuit. G infinity is the ideal transfer function when you let the loop gain t go to infinity, which you do so by letting the gain element, or one of the gain elements in the forward path, go to infinity. G0 is a transfer function when the loop gain t equals to 0, or when you make the gain element in the forward path go to 0. This is also referred to as the transfer function without feedback, but with the loading of the feedback. What that means is that when you set t equals to 0 by setting the gain element in the forward path equal to 0, you're killing the action of the feedback. That's why we say transfer function without feedback. But while you kill the action of the feedback by setting a equal to 0, you are maintaining the loading of the feedback network on the original amplifier. Also, if you're working out a voltage gain or a current gain or a trans resistance or a transconductance of a feedback amplifier circuit, G0 is the amount of transmission that you get from the input signal to the response at the output, whether that's a voltage or a current, through the feedback connection when you kill the gain equal to 0. And finally, T is the loop gain. Now, each of these is going to be illustrated in diagrams in the upcoming slides. First, we review G infinity and G0. We said earlier to determine G infinity, we let the value of the gain element A inside the feedback amplifier go to infinity, and we determine the ratio of the response to excitation, UO over UN, with A equal to infinity. This reduces the calculation to that of an ideal op-amp circuit calculation that you may be familiar with. Likewise, we determine G0 by setting the value of the gain element A inside the feedback amplifier equal to 0, and once again we determine the ratio of the response to excitation with A equal to 0. Now that we've introduced the concept of loop gain as the product of A and its inverse, we can say that G infinity with A equal to infinity is actually G infinity with the loop gain T set equal to infinity. Likewise, for G equals to 0, we can say that it is the transfer function with the loop gain set equal to 0 instead of saying A goes to 0. So then G infinity, another way of looking at it, is the value of the transfer function with the loop gain equal to infinity, and G0 is the value of the transfer function with the loop gain T equals to 0. With the understanding that T infinity is determined by letting the value of the gain element go to infinity, and T equals to 0 is obtained by letting the value of the gain element go to 0. We are now going to see why the product A bar is defined as the loop gain T. We learned from the extra element theorem from dependent sources that A bar is determined first by setting the excitation equal to 0 and replacing the dependent source A, or the gain element A, with an independent version of it pointing in the opposite direction. Here UT is the independent version of the dependent source, and the negative sign indicates the fact that it is pointing in the opposite direction. Now after you do that, you determine the ratio U1 over minus UT, and that is the gain A bar. A bar, as we've said earlier, is the inverse with respect to A with the excitation equal to 0. Now we bring back the dependent source A, or the gain element A, back into the picture, and that has a gain A equal to UA over U1. Now we see that the product AA bar is equal to UA over minus UT, because U1 cancels as shown here. So clearly, AA bar is the gain that the signal minus UT experiences as it goes around the loop and comes back to the point where it originated from. And that's why we call the product AA bar the gain of the loop, or the loop gain T. Now this figure suggests that if you want to determine the loop gain, after you set the excitation equal to 0, you break the loop immediately after the dependent source A, and you inject the signal at the right breakpoint and see how it makes it back to the left breakpoint. And that ratio, UA over minus UT, is clearly the gain of the loop. Now the problem with that is, in an actual electronic system, the gain element A comprises either a bipolar transistor, or a FET, or a JFET, or a MOSFET, and all those are active devices which need to be biased at a given operating point. So when you break the loop, you're going to lose that operating point. So breaking the loop actually in a physical system is not tenable, because you lose the DC operating point of the gain element. A better idea is shown here, where we inject the signal immediately after the dependent source A. We can always do that with a network analyzer in the laboratory. And when we inject the signal U in, we can determine the ratio of UX over UY, which is the loop gain T, with a minus sign in front of it. So this would be the practical way of determining the loop gain, and not by breaking the loop. Let us now introduce the concept of loop gain in the first feedback formula and the first feedback block diagram that you studied in school. So we set the excitation to 0, and we break the loop just before the feedback block H, and we introduce a signal UX into the feedback block H and watch it go around and come back to the same point where it originated from. And now UX over UY with a minus sign in front of it is the loop gain T. We can also introduce the concept of injection that we talked about and insert a signal U in, or inject a signal U in, just before the block diagram H, and determine the ratio of UX over UY with a minus sign in front of it, and that is going to be the loop gain T just as well. Let us now go back to the feedback formula GF equals to G over 1 plus GH and identify the loop gain T in it. We can do so by multiplying up and down by H and recognizing that GH is the loop gain T, so that this formula now can be written as G infinity times T over 1 plus T, where G infinity is the ideal closed loop gain that we get when T goes to infinity. Now we see that the second term of this general feedback formula, G0 times 1 over 1 plus T, is missing. And the only reason for that is this simple feedback block diagram does not have a direct path from the input to the output. The only path that it has is through the main amplifying path, which when you set equal to 0, that is to say, when you make the loop gain T go to 0, the output signal will go to 0. But we know in any real amplifying electronic system, there is a certain amount of gain that we have from the input to the output through the feedback connection, which we determine according to the extra element theorem by setting the value of the gain element in the amplifying path to 0. Now we can capture that on this block diagram by adding a block F, which directly couples the input to the output as shown. And now for this block diagram, we can write the closed loop gain equals to the original loop gain G over 1 plus GH plus F over 1 plus GH. And it is this one that corresponds to the general feedback formula. G infinity times T over 1 plus T plus G0 times 1 over 1 plus T. Once again, notice here that as T goes to infinity, the closed loop gain goes to the ideal closed loop gain. And you make T go to infinity by making the value of the amplifying element inside G go to infinity. And when we let T goes to 0, this term disappears, and the closed loop gain corresponds to G0, which is the amount of gain that you get from the input to the output when the gain element goes to 0, and that represents the amount of gain that you get through the feedback connection in a real amplifying electronic system from the input to the output. We're now going to summarize the augmented feedback block diagram for Middlebrook's feedback formula. The closed loop gain GF equals to G infinity times T over 1 plus T plus G0 times 1 over 1 plus T. We're going to do so by showing the three components of this formula, G infinity, T, and G0, on the augmented feedback block diagram. For the loop gain T, we have this picture. We set the excitation equal to 0, and we inject a signal at the input of the feedback block H. And we determine the ratio Uy over Ux with a minus sign in front of it, and that gives you the loop gain T that you have here. G infinity is determined by letting the gain G go to infinity in the augmented feedback block diagram, and you determine the ratio of the output voltage to the input voltage, and that is the ideal closed loop gain G infinity. And finally, to determine G0, we simply set the value of G equal to 0, which makes the loop gain go to 0, and you determine the ratio of the output voltage to the input voltage. We are now going to get a second formulation for Middlebrook's feedback formula by introducing the null loop gain Tn. We'll do so by first factoring out G infinity and obtain this form here, and then we divide up and down by T, and we obtain this form here. In it, this one will be defined as the reciprocal of the null loop gain, and this here will be the second formulation of the closed loop feedback gain given by Dr. Middlebrook. Tn is known as the null loop gain. In the next slide, we'll see why we call this the null loop gain. When we write Middlebrook's second formulation for the closed loop gain of a feedback amplifier next to the gain given by the extra element theorem for dependent sources, we can clearly see why Tn is called the null loop gain. It is called the null loop gain because it is the product of the gain element A with its null inverse gain, and T, as we said before, is the product of the gain A with its inverse gain with the excitation set equal to 0. That's the only reason we call this the null loop gain. Now that we have established a correspondence between the feedback formula given by the extra element theorem for dependent sources and the second formulation for the closed loop gain of a feedback amplifying system given by Dr. Middlebrook, We can show the determination of the null loop gain on the general diagram of a feedback amplifier system, whereby we inject a signal directly at the output of the gain element A and we null the response U0. We can do so by the simultaneous injection of the input signal and the injected signal here. Together they can null the response U0. Once you do that, you determine the ratio of Ux to Uy with a minus sign in front of it, and that gives you the null loop gain Tn. The ordinary loop gain T, we've discussed that before. We set the excitation equal to 0, and we inject the signal directly at the output of the gain element A, and we determine the ratio of Ux to Uy with a minus sign in front of it, and that gives you the ordinary loop gain T. This summarizes the loop gain formulation of electronic feedback amplifiers. So what do you do with the augmented feedback block diagram? I say study it as an exercise in making block diagrams. It is a good mental exercise. In this case, you learned how to model the forward transmission through a physical feedback connection by augmenting the simple feedback block diagram with a forward block. Once you're done with that, forget it and do not try to force an amplifier circuit into that diagram. In other words, do not try to determine the blocks F, G, and H separately for a given amplifier circuit. Instead, master the extra element theorem for dependent sources and use that for the analysis of all feedback amplifiers. In the coming few lectures, I will work out several examples of loop gain analysis. Thank you.